in a series of videos about continuity, and we talked about in class the notion of what it means for a function to be continuous, and I want to emphasize that we'll always be talking about continuity at a particular point. So we might say a function is continuous at the point, x equals 5 or the point a equals 5. And so we're always going to be interested in behavior locally near that point. And the basic idea is that a function is continuous at some point in its domain if points really close to that input get mapped to points really close to that output. So let's sort of see what this means. So here's a graph of some function that I drew, and we've got this point A. So we want to say, what does it mean to be continuous at A? Well, intuitively, using what we know from maybe a calculus class, the graph is nice and smooth and connected, so we think it's continuous at A. And the reason for that is if I take a point near A, like say this point x here, well, if I plug that into the function, well, the function value didn't change much, right? We went up a little bit. We went from f of A up to f of x. But the point is if we wanted to make these points closer together, then the function values would get closer together. Right? So this is sort of the first example of a continuous function. One thing you need to be a little bit careful about in these problems is here's another function. It looks completely continuous. Here's our point A, and we see that if we move just a little bit to the left, right, this is really a tiny distance here, the amount that the function value has changed has been a lot, right? And so in the second video, when we talk specifically about what we're going to mean to say that a function is continuous, we're going to have to say, well, how close do the outputs have to be and how close do the inputs have to be, right? And you could imagine a function with a really steep slope. You may have to get very, very close to that point A in order for your function values to be close to one another. Here's an example of a function that's not continuous at A. So here we see f of A is over here. And the reason it's not continuous is because there are some points that are, if we pick a point to the left of A, well, then actually the output's going to be exactly the same as f of A, right? So if we think about what f of x versus f of a, well, they're going to be the same if I pick any point x to the left. But if I pick any point to the right, for instance, here this point y, well, if I plug in y, I get way up here on the graph, right? And so these aren't going to be close at all, right? And a good question you may have now is you may say, well, what if this graph up here I didn't label in numbers? What if this is only, this distance between these two line segments is just 1/2? Well, wouldn't that still be close? Well, we'll see in the definition. The point is that we want to be able to make things as close together as possible. So we're going to see, just like with definition of limits, there's going to be epsilons, and we want our basically we want something to hold no matter what threshold we choose. So we're continuing now. There's just one example I want you to be a little bit aware of. So if we look at this function here, look at the domain. So every function that we're ever going to talk about, we always have to specify what the inputs are. And typically the outputs are always going to be able to be the real numbers. That doesn't matter so much. But for this function, the inputs are just going to be in the interval from 0 to 1 and then from 3 to 4, right? So intuitively, we look at this and we say, well, if this were a bridge or something, it's definitely discontinuous. There's no connection between these 2 points. But in this class and in mathematics, it actually is a continuous function. And I want to talk a little bit about why that's true. So again, when we say a function is continuous, we mean it's continuous at a particular point in its domain, right? So we can ask, well, is this function continuous at 1/2? Well, yes, here's 1/2, and it looks very continuous. Is it continuous at 3.2? Well, 3.2 is over here, and it seems continuous there as well. In fact, the only thing you might worry about is, well, maybe is it continuous at 3? Well, let's see. Well, let's look at points in the domain that are close to 3. Well, the only points in the domain that are reasonably close to 3 are going to be things like 3.1 or 3.01, and those outputs are actually going to be pretty close to the function value of 3. Right? So if we plug in inputs, which mean things in the domain that are close to, say, 1 or 1/2 or 3 or 4, then we're always going to get outputs that are close to the values at those points. So this is a continuous function. So that's something to be aware of. And just a preview, I'm going to end this video now, but in the next video, I'm going to do 2 proofs. I'm going to introduce the delta and epsilon definition of continuity. And we're going to use that definition to prove that some simple functions are continuous at a certain point. So here's a function f. It's a quadratic function, and we're going to prove it's continuous at a equals 3. So it means it's continuous at the point 3, 5. And then we're also going to do a linear function. I think we'll probably do the linear function first, so the function 3x minus 5, and we're going to show that's continuous right here when x is 2 and the y value is 1. So please remember, feel free to email or come to office hours if you have any